It involves an understanding of processes, both present day and those that acted in the past. It involves the interpretation of rocks, the origin of sedimentary rocks, the depth of water that they originated in, the origin of metamorphic rocks, the kinds of pressures and temperatures that they were subjected to, the origin of igneous rocks, where they crystallized, how fast they crystallized, at what depth, and where they came from. It's very much the climax of a great deal of geological detective work. And in Canada, it's the climax of one of the most complex geological detective stories that is possible, because Canada's geology includes a large area of shield. It seems very flat and uninteresting at first, but as well as yielding very much of Canada's wealth, it also yields a great deal of data about the history of continents, not just Canada's history, but the history of continents as continents. Basically, it depends on the interpretation of the age of a rock, the recognition of the ages of rocks. One of the most complex problems of the 60s, which was solved by radiometric dating. The first part of the coming hour is a Planet of Man program, the Shield of Plenty, which deals with the fact that Canada's wealth is largely found in its shield, and the second part of the hour deals with the interpretation of the geological history of that shield.
This bay in which we're moored is typical of much of northern Ontario and indeed northern Canada, and such rocks occur in the heart of every continent. They're called Precambrian. You'll notice they're not flat and uniform, but they're red, granitic, and contorted. They're the oldest rocks in the world, and they take their name from the fact that some ancient rocks, about 500 million years old, were first found in Wales, called Cambrian, after the ancient name of that country. And all older rocks, older than 500 million years, are now called Precambrian. These are Grenville rocks on the shores of Lake Huron in Ontario, and were formed about 1 billion years ago.
Iron ore, gold, uranium and nickel, platinum, silver, lead, zinc. Mineral resources that build the foundations of modern industrial economies. Mineral resources from the oldest rocks on Earth, rocks of the Precambrian. Precambrian? Before the Cambrian. The Cambrian is the first geologic period whose rocks contain easily identified fossils. Cambrian fossils are about 600 million years old. From the Cambrian, then, to the present is 600 million years. Precambrian, all the time, and all the rocks from 600 million years ago to 4.5 billion years ago. Precambrian rocks are found throughout the world. Most of them, 17% of the total land area of the Earth, form extensive shields in every continent. The Canadian Shield, South American Shield, the Baltic, the African, the Indian, and the Australian Shield. In almost every case, the shields are formidable places. Difficult to penetrate and hard to live in. Sometimes, only the lure of possible mineral wealth draws people into this world. Apart from the shields, Precambrian rocks are found at the bottom of deep gorges, like the Grand Canyon, where erosion has cut away the younger rocks. And some are at the base of mountains, like the Sandia Range in New Mexico. The rocks of the Precambrian. It's only in this century that the almost unbelievable duration of Precambrian time has become clear. Around the turn of the century, it was thought that the Precambrian was relatively a very short period of time, and the Earth itself was believed to be only about 40 million years old. In the first 20 million years, molten rock was supposed to have cooled and laid the granite foundations on which Cambrian and later rocks were built. The evidence found in Cambrian and later rocks, however, made this theory unacceptable to geologists. The theory failed entirely in accounting for the great thickness of rocks deposited since Precambrian time. The 20th century has confirmed the geologists' doubts. By 1917, the estimate of the Earth's age had increased to 1,500,000,000 years. By 1947, this figure had jumped to 3 billion years. Now, the Earth is estimated to be 4.5 billion years old. It's not easy to grasp a billion. It may not even be possible. But if we can suspend our disbelief, the nearly 4 billion years of Precambrian time must surely be a haunting mystery for mankind. The mystery of his origin. Today's best guesses suggest that our world began about the same time as our solar system, 4.5 or 4.6 billion years ago, when a cloud of dust and gas pulled itself together into a sphere, the Earth. Precambrian time extends from that event forward 4 billion years. Precambrian is not an expression, a couple of days or a few years. It's 88% of the entire history of the Earth. It is awesome. It is fascinating. It is frustrating. Historical evidence for all of the Precambrian is not available. It is perhaps lost forever. The oldest rocks found on Earth up to now are 3.8 billion years old, so that the Precambrian's first 700 million years are not documented. And these oldest rocks are hard to assess. In the history of geology, information about the Precambrian and the techniques of getting that information are relatively new. Precambrian rocks, found in some of the most inaccessible and most inhospitable places on Earth, have given up their secrets very, very slowly. Some of the information came accidentally, as a byproduct of other operations. When the Canadian Pacific Railway was built, many of its critics scoffed at the foolishness of trying to build an all-Canadian route, which meant passing through the Precambrian rock north of Lake Superior. But it was the all-Canadian route which opened up Sudbury and led to the discovery of the nickel and copper deposits of the Sudbury Basin. And there's the grand old story of Fred LaRose, a blacksmith working on the Temiskaming and Northern Ontario Railroad. Fred threw his hammer at a fox, but he missed. Instead, he uncovered a rich vein of silver ore, and the LaRose mine at Cobalt was soon in operation. The early discoveries of ore bodies led to systematic prospecting, and such prospecting throughout the world led to the realization that the Precambrian rocks are a treasure house of mineral resources. In Canada, the iron ore deposits of Labrador, the gold mines of Northern Ontario and Quebec, the uranium mines of Ontario and the Northwest Territories all belong to the Precambrian. And in South Africa, the Rand gold mines, situated on the largest gold deposits in the world, take their wealth from Precambrian rocks. In Brazil and Sweden, rich iron mines have been developed in the Precambrian. All over the world, the minerals of the Precambrian have led to its investigation and its unmasking. But to find the rich ores, geologists and prospectors have to know where to look. And in one major respect, the Precambrian makes the search difficult. Fossils in Cambrian and later rocks provide geologists with a very reliable tool for dating and correlating them. But the generally primitive, one-celled organisms of Precambrian time have disappeared almost without trace. A few clues remain. Stromatolites, the fossils of blue-green algae in the Northwest Territories. Some possible worm burrows in Australia. But the finds are generally too limited to be useful in documenting Precambrian rocks. In the absence of fossils, another useful technique has been developed to date rocks. Called radiometric dating, it relies on predictable rates of radioactive decay in certain elements as a guide in determining the age of rocks. For example, some uranium decays at a known and predictable rate to lead. With radiometric dating, the ages of rocks containing both uranium and lead can be established with a fair degree of certainty. In Canada, these techniques have enabled geologists to develop a useful date map of the Canadian Shield, information of major importance for mining prospectors. There appear to be two broad time divisions within the shield, the Archean and the Proterozoic. The Archean areas, or provinces, are the oldest Precambrian rocks. The Proterozoic provinces are the later Precambrian rocks. On the ground, the age differences between the provinces of the shield can be dramatically emphasized. For example, the McDonald Fault stands out quite clearly as the boundary between the Archean Slave Province and the younger rocks to the south. Usually, however, the boundaries between the provinces are much less prominent. Two of the Canadian Shield provinces, Superior and Slave, belong to the old part of the Precambrian, the Archean. These Archean provinces are characterized by the so-called Greenstone belts, composed of volcanic and sedimentary rocks. A typical greenstone belt might be 40 kilometers wide and 400 kilometers long. How these belts were formed remains a part of the Precambrian mystery. But whatever their origin, their commercial value is beyond doubt. Much of Canada's silver, 30% of her copper, and 40% of her zinc comes from these greenstone belts. So, an exploration program in the older Archean provinces in search of silver or copper or zinc naturally concentrates on the greenstone belts and not on the terrain around them.
Get the handle on and start turning it. It's open now. Rotate the handle.
This isn't the case in the younger provinces of the Shield, where there are no greenstone belts and minerals are more generally distributed. This difference in the rocks of the Archean and Proterozoic is apparent in shield areas throughout the world. It suggests very strongly that an important change in the Earth's geological processes occurred at the end of Archean time.
Said in the letter that it was available for 24. Churchill, what's your weather today? You mentioned when it would be ready as far as the twin otter is concerned. The single otter, he said would probably be ready on the 22nd, but he wasn't exactly sure on, as far as the single otter is concerned. Yeah, okay, yeah, sure, why not?
How many loads do you figure we have to take out? 4 to 6?
We got, at least, I'd say 6 at least.
In the Proterozoic provinces, mining geologists are likely to search for ores in the thick sedimentary sequences deposited on the margins of fold belts. Sediments like these contain Canada's major uranium ores, much of the world's iron ore, and the Rand gold deposits of South Africa, the richest in the world. An understanding of this fundamental difference between the Archean and Proterozoic is all important for successful exploitation of Precambrian mining potential. Possibly, probably, perhaps. Common words in any description of the Precambrian. It's impossible to be certain about this 88% of the Earth's history. The evidence is only fragmentary. In the Shield's older provinces, huge expanses have been planed almost smooth by billions of years of erosion. Where volcanoes or mountains may have stood, even their roots have disappeared. At the bottom of the Grand Canyon, between the Precambrian rocks and the next layer above, 1/2 billion years of geological history are missing. Even where the old rocks remain, their nature has sometimes been altered drastically by heat and pressure, so that they are difficult to interpret. The oldest known rocks were originally sedimentary. This means that, even then, there was water for erosion and seas in which sediment could settle, just as mud and silt do today at the mouths of rivers and in the oceans. This process of erosion and sedimentation continued throughout the Precambrian, and one group of sedimentary deposits, the Elliott Lake uranium ores, provide evidence for an important theory, as explained by David Pearson of Laurentian University.
This is uranium ore, and that's the sound that made a prospector very happy and might have made him very rich. The ore consists almost wholly of rounded quartz pebbles and quartz sand grains. Only 0.1% is the uranium ore mineral brannerite. Such rounded quartz pebbles and quartz sand grains are typical of beaches at the present day. But if you took such a mixture of quartz pebbles and grains and uranium ore mineral and placed it in a place where it could be washed by waves, you would find that although the pebbles would survive, the uranium ore mineral would be very quickly dissolved. And this, of course, raises the question of what's the difference between the present day and the past when this ore originated. The answer probably lies in the atmosphere. Today, oxygen is very important. We all breathe it. But in the past, there was very possibly no oxygen in the atmosphere, and therefore no oxygen dissolved in the seawater which washed these pebbles and the uranium mineral around on the beach. And it seems that the rivers draining the hinterland, the granitic hinterland, were able to bring with them, as well as quartz pebbles, tiny grains of uraninite and brannerite, the uranium ore minerals, and they were able to survive the washing around on the beach to become incorporated in this conglomerate and become the Elliott Lake and Denison uranium ores.
If there was no oxygen in the Precambrian atmosphere, oxygen which is essential for life on Earth today, the search for life in the Precambrian would seem hopeless. But clear evidence of life can be found in the Precambrian. Stromatolites, probably early algae, here built into limestone reefs, have been dated in the last billion years of Precambrian time. And evidence from South Africa shows that life may have existed as much as 3.2 billion years ago. Geologists have used all these pieces of fragmentary evidence to develop hypotheses about the beginnings of life on Earth. One theory suggests that the Earth developed an atmosphere of water vapor, ammonia, and hydrocarbons, such as methane. In this environment, which had no free oxygen, primitive one-celled organisms developed, living their short lives and disappearing. They lacked the hard shells or skeletons to be preserved as fossils. Some of these organisms probably produced oxygen, as do plankton in the sea today. Ultimately, other organisms probably became capable of using this oxygen. When this occurred, animal life began, as we know. However, if such an evolution took place, it is not known how or when. The rocks of the Precambrian provide only fragmentary clues. But because they are the only clues, these rocks are extremely important. With the development and use of radiometric dating techniques, surer correlations of rocks can be established. And a better understanding of the ages of Precambrian rocks will assist not only in commercial mining ventures, but in our grasp of the history and nature of our world.
It's okay, I didn't think of it. Maybe about 5 days, then you want to flown over to New Zealand, I reckon the 16th, and then roughly 20th or so, but to come back here across the bay with the boat. And we've got enough food, and I asked Bob that when the chopper comes over to move us from Southern to Hammonack, and he'll throw in a care package. Oh, you got enough fresh meat for 5 days.
The job of reconstructing the Precambrian isn't easy. The fossils are few and far between. Great gaps exist in the rock record itself. And all theories remain tentative until more pieces of the puzzle can be found. It's likely that the Precambrian will never yield its final secrets. But our quest for minerals will make detectives of science and industry long after the trail grows cold.
The geological anatomy of Canada, the way the mountain belts and the flatter, more stable areas of the continent are arranged, is typical of most continents. What is not typical is that the rocks, the bedrock in Canada, is generally speaking very much better exposed than the bedrock of most other continents. And the reason for that is the last ice age. The ice of 10,000 years ago simply cleared off a great deal of the soil which normally covers the bedrock of most continents. So Canada is a good place to look at, or a good place for a case study of the geological makeup, the geological anatomy of continents. Now, the tools which geologists use in order to interpret the anatomy, the geological anatomy of an area, whether it's a continent or a township, are geological maps. And a geological map consists of a normal geographic map on which geological data have been plotted. And the kind of data which are plotted on the map are things like dip and strike, which gives the orientation of the rock which a geologist is observing, and then also the rock type, whether it's a sandstone or a limestone or a shale or a granite or a basalt or whatever. This is also recorded on the map. And then finally, if it's possible, the age of the rock, not in years, but in the system to which the rock belongs. Now, this is, of course, not very often possible with something like a basalt or igneous rocks, which have to usually be dated radiometrically, but it is commonly possible with sedimentary rocks. So that's the kind of data which goes onto a geological map, whether it's a map of a continent or a township. Let's have a look at a map of a continent, of Canada. The first thing which is obvious on this map are the areas of different colors. Now, colors are used generally to represent rock of different type or rock of different age. It's rather like putting together a picture by numbers. The kind of rock is represented by a particular color, or the age of rock is represented by a particular color, and all the places where a geologist finds rock of the same age or the same type are joined together, and what results then are areas, patches, bands, or whatever of the same color. That's easily visible on the map. Let's have a look at it. Here is a blue band lying on the southwestern shore of Hudson's Bay. That blue band represents Ordovician strata. Here is part of the Canadian Shield, which is pink, dominantly pink. That pink represents granitic rock. Here, around Lake Winnipeg, more of a blue band, again, Ordovician rock. Here, a slightly different color, gray, Silurian, a light blue, Devonian, and away across the prairies, this green color, this very broad band of green color, is Cretaceous rock. And then into the Rockies, once again, blues, Ordovician, reds representing granites, greens representing Cretaceous, more red around the area of Vancouver, representing again granite, and out to Vancouver Island, more greens and reds. That kind of geological information, the age of rocks plotted according to color, is also done on entirely different scales, of course. In this map of Pennsylvania, where the scale is 1 inch to 4 miles instead of 1 inch to 80 miles, as it is on the map of Canada, the different rock types, which is what these colors represent, are also arranged in a pattern, in a very, very clear pattern. Now, what do those patterns represent? What does that bird's eye view of the geological surface of Canada or of Pennsylvania represent? What produces those patterns? Well, to answer that question, we must look at the effect of erosion on geological structures. remember that one of the most important structures in the Appalachian Mountains are folds, anticlines and synclines. Now, what happens to a fold when it's eroded? Well, let's do that with a Pleistocene model. This is an anticline, each of the different layers of Pleistocene representing a different rock type. Now, to erode it, we would do something like this. In other words, take off the top of the anticline. What are we left with on the eroded surface? We're left with a parallel arrangement of bands of different rock type. If you were to date by collecting fossils, if they were sedimentary rocks, those bands, we'd find that the oldest was in the center, and then on either side, younger rock, farther out, younger still, and farther out, younger yet again. So there's a very definite pattern to the surface produced by erosion of an anticline, and the same thing of a syncline. Looking back at that map of Pennsylvania, I think that you can recognize the synclines and the anticlines of the Pennsylvania area eroded down to the same kind of pattern as we produced in the Pleistocene model. Faulting, as well as folding, also produces patterns that are recognizable on an eroded surface. Let's look at this model. Here is a surface pattern of some simply dipping strata. The oldest and then successively younger strata lying on top of it. Now then, let's fault with a normal fault that area. There's the fault, erode away the higher land. There is the pattern that's produced. Notice that the fault runs parallel to the strike of the strata. In other words, parallel to the orientation of the individual beds. Notice that the yellow bed here is repeated on the other side of the fault. Then the red and the successively younger strata, one after another. And right at the fault, young rock is present against older rock. The yellow stratum originally lying beneath the grey one. Let's have a look at another kind of fault in the same sort of terrain. Once again, a simple surface pattern, simply dipping strata, the oldest and then successively younger strata on top. This time, the fault runs at right angles to the strike of the strata. In other words, it runs across the pattern that's faulted. And she goes. Erode away the higher land. There is a pattern that's produced. Strata are displaced from one side of the fault to the other. Now, we could go on with different combinations of faults and folds and different kinds of faults and folds and produce different kinds of patterns. But you can see, I think, just from those few examples, that the bird's eye view of patterns of strata on a geological map reflects the history, the geological history of the area. From the pattern, we can interpret the orientation of the strata, we can interpret the kinds of faults and the kinds of folds. A very, very important tool in diagnosing the geological anatomy of an area. Now, we can't do that on the geological map of Canada because the scale is unfortunately too large. There are too many miles to the inch, so to speak, to see the kind of detail that we've been talking of. But let's go back to the map of Canada, back to greenstone bolts. Now, you'll remember from the film that greenstone bolts lie in the granitic areas of the shield. Let's go and look for them on the map. The major part of this map, the pink part, is the shield area, the granites and highly metamorphosed gneisses and schists. And the greenstone bolts lie right here in this kind of position. They're the relatively dark bands running approximately east-west in this area, southwest of Hudson's Bay. Now, greenstone belts are still very enigmatic features. We don't really yet know the origin, but they are relatively easy to recognize when we find them in the field. They're characterized by very particular, easily recognizable rocks. One of those is iron formation that you've already met, characterized by alternating red and black bands, rich in silica and iron oxide. But it's basalt which is the most typical rock of greenstone bolts, and in fact the green color of the slightly metamorphosed basalt is what gives greenstone bolts their name. This is a complete pillow of pillow lava basalt. Here the smooth surface of a pillow, and on this other specimen you can see the outlines of the pillows. One of the best exposures of pillow lava is in the Yellowknife area of the Northwest Territories, where very beautiful and very large pillows are exposed. Now, you'll remember that pillows are produced when lava flows out underwater, so it isn't surprising that occasionally in some outcrops one finds lava and sediment associated in the same outcrop, as in this one described by Dr. Riddler of the Geological Survey.
We have here a flow top contact between a lower flow and an upper flow, separated by a series of well-banded chemical sediments. A chemical sediment being one which has precipitated out of solution from seawater. The lava flows are probably basaltic in overall composition. The chemical sediment is composed of light weathering chert bands and dark weathering iron carbonate bands with some magnetite.
It's easy to see that the greenstone bolt rocks, both the lava and the sediments, originated in water. But beyond that, we still really don't have very many answers. One suggestion is that the greenstone bolts originated as troughs on a thin granitic crust. Let's have a look at a diagram which shows that situation. Here is the situation in which the greenstone bolts may have originated. Imagine this green area as a trough, perhaps 10 or 20,000 feet of lava and sediment accumulating in them, and the lava lying on a thin crust of granite, much, much thinner than at the present day. Remember that the greenstone bolts, as you saw in the film, are found in Archean areas, that is, rocks which are older than 2,500 million years old, and the crust of the Earth was probably very different then. The source of the lava indicated here, probably from a basaltic layer lying beneath that granitic crust, and the granitic crust thought to have originated by differentiation of the basalt. You remember the separation out into rocks of different kinds from a basalt magma. And then through the course of time, it's thought that the crust, the granite crust, thickened by the addition of granitic material to the underside as the crust cooled. And in this way, the greenstone bolts came to lie within the granitic crust that we find in the shield at the present day. Now that's just one suggestion. There have been a number of others, but that's probably one that's quite widely accepted, but by no means unanimous. Now, the granitic areas of the shield, of this pink area on the map, also have their puzzles. Since about 1950, divisions have been made in the granitic shield. Let me put those on. A division has been made here, another here, and another in there, another important one here, and a small one in there around the Sudbury area, another important one here, and finally another boundary in here. So that the granitic part, the dominantly granitic part of the shield, has been divided into a number of units. What characterizes those units? Well, what characterizes them is the age of the igneous and metamorphic rocks, and that age indicating the time at which the dominant igneous intrusions crystallized and at which the last dominant metamorphism took place, and both of those indicating the time at which the granite was last, if you like, mobile. And remember that above this granitic shield were probably at one time quite high mountains, and so the age of the intrusions and the age of the metamorphism reflects the time at which mountains were being formed in that particular part of the shield. And the ages differ. The oldest are between 2.5 and just over 3,000 million. The youngest about 2,000 million. If we pick those that are or have ages of 2,500 million and over, we find a very interesting picture. Let's have a look at a diagram which shows that. This is the eastern part of Canada. Here the Great Lakes, here the St. Lawrence, and here the Arctic coast. And the orange patches reflect areas within the shield where we find old rocks, rocks older than 2,500 million years. And you'll notice that they're in relatively coherent units. Here quite a small one, here a much bigger one. In other words, they're not little patches everywhere, but they're quite large areas. And we think that these are probably what have been called proto-continents. They are the first sign of bodies of granite on the surface of the Earth, which later coalesced to form the shield areas at the nucleus of all continents. So this is the stage in the evolution of the Canadian shield about 2,500 million years ago and more. Between those proto-continents are areas of younger rock, 2,500 million years and younger, and lying on the edges of the proto-continents are quite commonly sediments, and those sediments lie unconformably on the edges of the proto-continents. And let's have a look at such an area in the field where sediments lie on the edge of the proto-continents. This is a typical boundary found near the west coast of Hudson's Bay. The Proterozoic is represented by the well-bedded strata in the foreground, and the Archean rocks are the massive rocks against the skyline behind Rowley Riddler of the survey.
I've just come walking down a little gully which represents the surface between two groups of rocks representing the loss of several 100 million years of Earth history. This surface is known as an unconformity. The rocks on my right are a series of sandstones, water-lane clastic sedimentary rocks, which have been metamorphosed and folded, and as you can see, dip off gently to my right at 45 degrees. The rocks on my left are much, much older. They're quite massive and show quite a distinct contrast with the much younger rocks on my right.
Don't overlook what those sediments indicated, those Proterozoic sediments. Earlier sediment had accumulated together with lava in rapidly subsiding greenstone bolt troughs. Those sediments, those Proterozoic sediments, accumulated on the edge of a proto-continent. And for sediment to accumulate on the edge of a proto-continent, the continent must have been thick enough, rigid enough, and strong enough to support those sediments the same way as the continental shelves of the present continents support sediment. The Elliott Lake sediments were deposited in a similar position on the edge of a proto-continent. And one of the best areas which shows the change in the behavior of the continental crust is in the Great Slave Lake area between Yellowknife and the Arctic coast, as described by Dr. Hoffman of the Geological Survey.
Here we have the thin and very gently dipping sediments which are deposited on the Archean basement, the older Precambrian basement, which is exposed out in the hills over there where these beds have been eroded away. These beds were deposited unconformably on the Archean basement, but they're very thin here, although they thicken as you go westward. And you can trace these same beds thickening westward for about 60 miles, still resting on the Archean basement, and then the Archean basement disappears as you go over what presumably is the edge of the Archean continental shelf. And these beds are all shallow water beds deposited on the continental margin, on the shallow water shelf at the continental margin, and about 60 miles to the west of us, these go into a much deeper water facies as we go off the edge of the continental margin out into the continental rise and the deep water sediments to the west.
Those limestones are some of the first marine limestones deposited on the edge of a continent. And as you look west here, you're looking out across what was once one of the first continental shelves in the geological record. Those limestones have now been stripped away, and what one's seeing is the granite of the proto-continent on which the sediment was originally deposited. One of the indicators of the environment in which that limestone was deposited, which indicates it was shallow water, like the lagoons of continental shelves, are the fossils, and in particular the stromatolites, the fossil algae, which we've already met when we were looking at fossils. This is a specimen from the Great Slave Lake area. There are some areas along the shore of the lake in which very, very beautiful specimens can be seen, eroded away just now as they once were, but remember that they're nearly 2,000 million years old. Those cabbage-like heads are a kind of a fossil algal garden, once covered in 10 or 20 feet of water. Algal growths similar to those preserved in the Precambrian rock record of Great Slave Lake are found living today in Great Salt Lake in Utah. There are a number of varieties of shapes, and this is one of the most important of them. The upper dark surface is a gelatinous film of filaments of living blue-green algae. It's only that upper surface which is living, and the algae trap particles of carbonate and build up this shape from a hard base. They always must start to grow on a firm base. And then as sediment builds up around them, they develop this kind of bulbous form. Breaking open the algal growth reveals the color of the internal part of the growth. Very white because it's only the upper surface which is living, and the main part is formed of carbonate mud trapped by the upper surface. And the upper surface then grows through that carbonate mud to produce a new surface. The layering isn't clearly visible in this particular growth. So both the fossils and the sediments indicate deposition in shallow water. Limestone is a typical sediment of shallow, warm water. And that's the kind of conditions that we find today on the continental shelves. So it seems that the proto-continents about 2,500 million years ago began to become rigid enough to develop continental shelves. The next phase in the story took place about 15, 16, maybe 1,700 million years ago, when the proto-continents seem to have collided and the Proterozoic sediments became deformed. Now, of course, the results of that deformation have been eroded away, and we're left only with the roots of the deformation preserved in the shield. But it seems that it was then that the shield became a solid, rigid unit. The kind of shield that we know at the present day, and the nucleus of the continent onto which the Appalachians in the east and the Rocky Mountains in the west became welded due to the influence of plate tectonics. You can see that quite nicely on the panel. The action of plate tectonics has caused the shield to grow. The mountain belts lie on the margin of the shield, and there's also a mountain belt in the north, the Inuitian mountain belt, which is split up amongst the Arctic islands. So the story that we can read in the anatomy of the Canadian part of the North American continent shows us that about 3,000 million years ago, what we had were proto-continents. Proto-continents that were then thin and on which greenstone belts developed. The proto-continents became thick and rigid due to the accumulation of material underneath them, progressive differentiation. Then they developed continental shelf type rigidity. Those collided, provide us with a rigid shield around which plate tectonics welded the mountain belts that we know today.
Observe a whale roundup in Manitoba as Inuit hunters capture white belugas during their summer migration, and see the latest in medical technology for pets on National Geographic Explorer tonight at 7:30, 6:30 Central.
This is TV Ontario, Channel 19 in Toronto, Channel 18 in London.
Only a fraction of art produced in Western society is made by professional full-time artists. Folk art, in contrast, is made by ordinary people And while it can have great aesthetic merit, it often serves broader purposes. In a multicultural society like our own, one important function is to express ethnicity and enhance group cohesiveness and solidarity. In this intensive case study, we will examine the unique folk art created by working-class blacks in New Orleans for Mardi Gras. In old New Orleans, black slaves were free on Sundays to sing and dance together in a field called Congo Square. After the slave rebellions of the mid-1800s, blacks were forbidden to assemble except on Mardi Gras. But they managed to keep their music, dance, and chanting alive by merging them with elements borrowed from American Indians. Today, New Orleans blacks, organized into tribes, still gather on Sundays to prepare for Mardi Gras and continue an old tradition. To the people of New Orleans, the celebration of Mardi Gras provides a dramatic way of expressing culture through the arts. Mardi Gras is celebrated on the last day before Lent, the period in the Christian religion stretching from Ash Wednesday to Easter, which is observed by fasting and penance and commemorates the Passion of Christ. Masks and costumes play a central role in the festivities. The choice of which mask, which costume to wear,